If you like this video, make sure to visit our Vimeo page and follow us to get the latest update.
Okay, so you guys already had statistics class, right?
Yes.
Okay. Can you quickly take me through what are all, I mean, what are the topics that were covered? I mean, like what and all you know in statistics? Okay, let me ask some questions.
Like analysis, like obtaining the mean, median, mode.
Okay. Okay, that is fine. Okay. So do you know what are the different types of variables?
We did univariate analysis, bivariate, and multivariate analysis.
Okay, that is fine. And then?
Types of data, qualitative, quantitative.
Yes, yeah, the types of variables. And then?
Chi-square test.
Okay.
Correlation.
Uh-huh.
And the distribution is like normal distribution,
Okay.
confidence interval.
Okay. That's good. Okay, yeah, that's fine. So yeah, I see most of the basic topics are covered. So today we will be starting with the machine learning concepts. So I think, I mean, it's the most hot topic in the market right now. So what do you guys know about machine learning? Like, what is your understanding of that term machine learning?
It's the language that is used for AI. That's something I know.
Okay.
I can say like machine has to learn from the prior knowledge of the data.
Okay. Yeah. Any other answers? Okay. So yeah, what you said was correct. So in machine learning, what we are basically trying to do is we are trying to teach the machine something, that we have some data and we have the results. So what we are doing in machine learning is we are trying to teach the machine, saying that, so for this input we have this output. So what it can do is we will train the machine on that, based on that data, so that in future if we get any new data, we want the machine to predict what might be the output. So in a nutshell, that's what machine learning is. Okay, it's not a language actually, but it's a process where we teach the machines using the data. Okay, so let me give you a very basic example. Okay, so for example, let's say we have a okay, so we have a small kid and we are trying to teach him how to walk. Okay, so what the kid actually does is it will look at us and it will try to, it will try to understand how we are doing that. Okay, we are walking and it will see that, and after that we will try to train the kid like how to walk. Okay, so now after a few days of training, the kid knows how to walk and it starts walking. Okay, and after a few days it might fall down, and after that it will get up and it will start walking again, and it will make a note that I should not make that mistake again. Like it might have made a mistake, it fell down. Okay, so it will make a note of that and it will try not to repeat that mistake. So in this process, what the kid actually did was, it was actually trying to learn based on the experience. Okay, so the machine learning actually works in a very similar way. Okay, so it will take the training based on the data, and if it makes a mistake, so it will try to correct that mistake, and going forward it will try not to repeat that mistake. Okay, so as the as the training of the machine or the model it goes on, I mean, as we increase the training of the model, the mistakes made by the model decreases and its accuracy actually increases. So just get a high level overview of this. So when we actually go and build the model, you will understand it. But yeah, so this is the way you can explain to a layman saying like what machine learning is. You can take the example of the kid and explain it. Okay, so machine learning is a very uh, it behaves in a very similar way that I just explained in reference to the kid. Okay, so we will train the model, and if it makes a mistake, it corrects it in the future and tries not to make that mistake again.
So the machine itself corrects itself, is it? Or as programmer, the data scientist would have to put in the correction
No,
feature?
you don't have to do anything. Okay, so it's all built in the models itself. So there are various machine learning models. So they are derived in such a way that if it makes a mistake, then that will be corrected, auto corrected. So you don't know actually, as a data scientist, yeah, you should know how the actually the algorithm is working, but you don't have to go in the backend and change anything because it's already predefined. The algorithms are already predefined. Okay, so we don't have to go and change anything,
Okay.
but you should know how the algorithm is working. Okay, so okay, so let's begin. You guys are able to see my screen, right?
Yeah, Excel
Yes.
work.
Yeah.
Yeah.
So yeah, before getting into linear regression, let me just explain a few terms before that. So in machine learning, we basically have two types of learnings. Okay, one is, so you can write it down if you want. I mean, these are very basic terms, so you might have, I mean, you will come across these terms a lot in the future. You can just make a note of it. Okay, so under machine learning, we have two types. One is supervised learning, and the second one is unsupervised learning. Okay, so what do I mean by supervised and unsupervised learning? Suppose, let's say, uh, okay, have was this discussed, like the type of variables, dependent and independent variables, in the statistics class?
No.
Okay, okay, anyway, I'll explain. Okay, so let's consider this a small data set. Okay, so here I have totally 5 variables: x1, x2, x3, x4, and x5. Sorry, my bad. X4 and y. Okay, so here all these are numerical in nature. So you know what are the different types of variables, I guess. Continuous and categorical. So continuous can be defined, I mean, this can be termed as numeric as well. Okay, categorical is nothing but it's a character. Okay, so basically there are two types of variables: continuous or numeric, or categorical and or character. Okay, so now if you see these variables, all these are numerical in nature. Okay, so this is the first thing that you need to check. What are the types of variables I have? Is it a continuous variable, or is it a categorical variable? Okay, and after that, so let's say I have this data x1, x2, x3, x4, and y, and now I have one more row. Okay, so here I know the x1 value, x2, x3, and x4 value, but I don't know the value of y. Okay, so what did I say? I mean, what machine learning was previously. So I will pass all these to the machine learning or a model, okay, machine learning model. So it will try to establish a pattern in such a way that, so okay, if x1, x2, x3 and x4 values are this, then y is this, okay, and it tries to learn that for all the known values. And for the fifth value, for which we don't know the value of y, so it will check, okay, the value of x1 is 2, x2 is 4, x3 is 5, x4 is 6, so what might be the value of y? So the purpose of machine learning model is to predict what is the value of y. Okay, so here what we are trying to predict is y, so y becomes my dependent variable. Okay, and rest of them becomes independent variable. I'm just writing it down so that if we guys want to make a note of it, you can make a note of it. Okay, so whenever you get the data, this is the first thing that you need to do. What is my dependent variable and what is my independent variable? Okay, in any data set, there will be only one dependent variable, and independent variables can be, I mean, it can be a number of variables, that doesn't matter, but there is always only one variable, which is dependent variable. Why do we call it dependent variable? Is because we are trying to predict the value of y based on these variables, right? So these are not dependent on any other variable, but my y is dependent on these variables. So that is why I will call my y variable as dependent variable, and rest all are independent variables. Okay, and how you can predict, I mean, what is your dependent and independent variables is whatever variable that you want to predict becomes your dependent variable. So here in this data set, I need to predict what is the value of y, right? So my y becomes dependent variable and rest all becomes independent variables. Okay, is it clear? Any doubts till now?
So all the values, if they are given of the variable, they become independent, right?
Not exactly. Okay, in this data set, suppose let's say I don't have this row. Okay, I have this data set. So my requirement is, if I get any new values for x1, x2, x3 and x4, I need to predict what is y. So let me give you an practical example. Right, in centimeters. Okay, so let's take a practical example. So I have a data set which consists of three variables: gender, height, and weight. Okay, so I have this data that gender is male and his height is 167 and weight is 60 kg. Similarly, I have the data for around 6 to 7 guys. Now, what if, I mean, you get a requirement saying that I want to build a model in such a way that if I know what is the gender and what is the height, I want to predict the weight. Okay, so that is your requirement now. So even though even though this data set contains all the values of gender, height, and weight, the requirement is in such a way that I want to build a model which will predict the weight given the gender and height. Okay, so can you tell me in this case what is my dependent variable? I want to predict weight based on height and gender. So what
Weight is the dependent variable.
Yes, exactly. So weight is my dependent variable, and rest like gender and height are my independent variables. Okay, is it clear the concept of dependent and independent variables?
Just thought here, Nikhil.
Yes.
If I am trying to see, now they can be interchangeable, right? Now if I am trying to figure out the gender
Yeah.
based on the height and weight, then
Yeah.
I can gender will become the dependent
Yes,
variable.
exactly. That's what I mean. Whenever, see, whenever you get a data set, before going into the model, always try to, check what you want to do with the data set. Like, what do you want to predict? So, if you want to predict what is the gender based on height and weight, then gender becomes your dependent variable. Similarly, if you want to predict height, then this is your dependent variable. Now, in this case, I want to predict the weight, so this will be my dependent variable. Okay. Okay, so this is clear for everybody, right?
Yes.
Yeah.
Okay, good. So the next is, so now let's come to this machine learning. What is supervised and unsupervised learning? So in supervised learning, we will be knowing what is my dependent variable. Like we know what we want to do with a data set. Like in this case, I want to predict the weight. Okay, for this case, this case I can consider that it as supervised learning. So I can use any of the supervised machine learning models on this data set. Suppose you don't know what is your dependent variable. In going forward, I'll be referring dependent variable as target variable. Just don't get confused. This can be called as that as well, target variable. Okay, so in supervised learning, I'll be knowing what is my target variable, but in unsupervised, I don't know what is my target variable. Okay, so under supervised learning, we have, let's see, many machine learning algorithms. So I'll just list them out. Linear logistic. Okay, so these are just few. Few of the. There are so many supervised learning models. These are just few of the examples that I gave. Okay, so in all these cases, I'll be knowing what is my target variable. But in the unsupervised learning, we don't know what is my target variable because we don't have like a perfect requirement. Like I want to predict weight or height. So that's where clustering comes into picture. So what do you mean by clustering is we'll just try to group similar objects together and we will try to define characteristics of that particular clusters. So for example, let's consider, okay, so I have this data set. So what I will do is I'll just cluster the data sets, all the data points into two clusters. In this case, you can cluster into as many clusters as you want, but in this case I'm just creating two clusters and I'm dividing the data points. Okay, so I have created two clusters and divided the data points. So what you can do with this is you can derive the specific characteristics for each of the clusters. So let's say uh, the cluster one, the characteristics could be most of the people lying in cluster one are males, or the average weight of the people lying in cluster one is like 60. So the average height is 160 centimeters. Okay, so in this case, what you're trying to do is, you're just trying to cluster the people based on the certain behaviors. So this is mainly used in what do you say, the retail customers. So, what the retail chain stores they do is they will cluster the people based on their purchasing habits, and they will advertise only that particular products to them. Okay, for example, let's say you go to a superstore and you purchase, like, let's say 1 kg of sugar every month, and suddenly after that for 2 months you don't go. Okay, so what they will do is they will check in which clusters do you actually fall. So they will go to that cluster and see what are the purchasing habits of that particular cluster. So let's say if you fall in a particular cluster, so the characteristics could be, so okay, so these people actually buy stuffs like sugar or only like not assets or not gadgets or anything, only home, what do you call them? Only household products, you could say. Okay, so they will take that information and they will, advertise only that particular, information to you. Let's say we are offering a discount on this particular product, so you are welcome to purchase that. So this is where the application of clustering comes into picture. Okay, so is it too much to take, or are you guys understanding?
Yeah, it's fine.
Yeah.
Okay, so don't worry
So
too. Yeah,
in
yeah.
real life, maybe there will be more clusters. Like,
Yes,
okay,
exactly. So
children,
if
teenagers,
yes,
family people, family with kids,
yes, exactly.
old, retired, like, okay.
Yes,
Got it.
as the customer base goes on increasing, the number of clusters actually goes on increasing. It's up to them, the owners, like how many clusters they want and what are they actually looking for, what are the information that they're actually looking for. Okay, so we will actually build them in the coming classes, but just wanted to give a heads up. Okay, so in the supervised learning, we have these many algorithms. Similarly, in the unsupervised as well, we have many algorithms like k-means, and then hierarchical clustering. Okay, so these are the main algorithms that we will be using for unsupervised learning. Okay, so any doubts till now?
No, Nikhil, you can proceed in my case.
Okay. Okay, so let's start with linear regression. I'll take the same example. So first, I'll just explain what is the regression, and then we will move on to linear regression. Okay, so okay, so I have a data set that consists of three variables: gender, height, and weight. So you know the data. I mean, you know the gender, height, and weight for all the like all these data points. But there is one data point like where I don't know the weight. I want to predict what is the weight for this. For this gender and this height. Okay, so now let's forget for this now. I mean, it will just make things complicated. So let's consider only 2 points, two variables. So one independent variable and one dependent variable. Okay, so I know the height and weight for all these data points, but there is one data point for which I know the height, but I don't know the weight. Okay, so in this case, how we can use, how we can try to predict weight based on height is, we will use a machine learning model called as linear regression. So, okay, before jumping into linear regression, let me just take you through something. Just stop me in between. I mean, if you guys are stuck somewhere, just let me know. Okay, so here let's consider height as x and weight as y, and let's just try to plot them on a two-dimensional graph. Okay, so for height 167, the weight is 160. Let's just randomly plotting them. Okay, so we have plotted all our data points. I mean, whichever for which we know the height and weight, we have plotted them on a two-dimensional graph, x and y. And now what we can do is, let's just try to establish a relationship between x and y. Okay, I mean, that's what we have done here. We are just trying to establish a relationship between x and y by plotting them in a graph. So this process of establishing the relationship between dependent and independent variables is called as regression. This process itself is called as regression. Okay, not linear regression, but just the term regression means establishing relationship between dependent and independent variables. Okay, so okay, now that you know about regression, in linear regression, what we will do is we'll just try to fit a line in such a way that it passes through as many points as possible. Okay, in this case, let's say, so what could be the line? This could be the line, right? So this is the line which tries to pass through as many points as possible. Yeah, there are some points, I mean, through which I cannot pass them. So this has to be a straight line. Okay, so this could be my, I mean, the best line that I could fit based on the, I mean, based on the condition that it's trying to pass through as many points as possible. Okay, so do you guys remember I discussed something about best fit line when I was explaining the graphs? Okay, no issues. So yeah, so this line which we fit, I mean, which satisfies that condition that it's trying to pass through as many points as possible. This line is called as best fit line. Okay, so how this line is actually derived, that we will see after a few, I mean, in the coming slides. But so that's how the linear regression works. Okay, so okay, now you know that based on these data points, you have fitted this line. Now, how can you use this line to identify what is the weight based on this height? Okay, so okay, you know the height now. So what you can do is, so let's say the height of 180 might be somewhere around here. Okay, so you draw a straight line where it touches this best fit line. Okay, so this is where this 180 is touching. Now you take this value and drag a horizontal line on y. Okay, so you got a value for y. So this is not, y is nothing but my height. Sorry, my bad, weight. Okay, so how we can use this line is, for this weight, I'll just draw a line which, I mean, which will find me a point on this line, and then I'll draw a horizontal line which will give me the weight. So that's how the linear regression works. It will fit a best fit line, and for a particular value of independent variable, it will get me the value of dependent variable.
So the dependent variable has to be a y or not?
Yes, I mean, that's how we actually plot it. That's how the linear regression works. Your dependent variable will always be on the y. All your dependent variables will be plotted on y itself. Okay, and your independent variables will be on x-axis. Okay, so clear with the, I mean, basic idea of linear regression. Now you guys must have got the idea at least.
Yes.
Okay. Okay, so let's start. Okay, so yeah, like I said, regression is a process where we will establish a relationship between dependent and independent variables, and yeah, that's it. So yeah, so that's the definition of regression, linear regression. Okay, so this line that that is fit, it's actually based on certain assumptions that we take on our data set. Okay, so let's see what are those assumptions. So the first one is linearity. So what do you mean by linearity is, let's see, I have around 10 data points. Okay, so oh yeah, so these are my data points. So the data points should be in such a way that as my x goes on increasing, y should also go on increasing. Okay, so the data point should not be like something like this, because if you see, when I go from here to here, my x is, I mean, as my x increases, y is also increasing. But after I pass this point, as my x is increasing, my y is actually decreasing. Okay, so this is not a linear relationship. So we cannot use such data, I mean, such data set to build a linear regression model. Okay, so always there has to be a linear relationship between my independent variable and dependent variable. Okay, so the relationship cannot be something like this, or something like this, or something like this. Clear? If you look at this, if you look at this diagram, you can see as my x goes on, y is also increasing. Okay, in the second diagram, if you see, as my x is increasing, y is decreasing, but that is fine. Okay, there has to be, when I say linear relationship, it can be either positive or it can be either negative. So what do you mean by negative is, my x is increasing, but my y is decreasing, but that is fine. There is there is at least a linear relationship. It can be either positive or it can be either negative. Okay, so if you see, this is, yeah, if you draw a straight line, you can consider it as a linear relationship. But here it's not a straight line, so I cannot say there is a linear relationship between them. So we cannot use such data points, to build a linear regression model. So in order to build a linear regression model, this assumption has to be satisfied, that my data is linearly, my dependent and independent variables are linearly correlated. Clear?
Not clear about the last, because even here, as the x is increasing, y is increasing.
Okay, so let me give you an example. That relationship is actually exponential, it's not linear.
Oh, got it.
Got it, right? So if you see,
Thanks. Yeah, so it's an
it's an exponential.
Thank you.
Yeah, no issues. So it's an exponential relationship, so we cannot use it. So, but this is a linear relationship, so this has to be satisfied. Okay, any other doubts? Okay, let's move on to the next assumption. Okay, normality of errors. Okay, so once a linear regression line is fit, so what that model will do is, it will calculate based on this line, based on this best fit line, So it will calculate a predicted value. So what do you mean by predicted value is, so after this line is fit, so let's say this is my best fit line now, okay, for that data. So once this line is fit, so what this model will do is, for this height it will calculate its own weight. It will not consider this for now. I mean, it used this actual weight to fit this line. Now what it will do, it will calculate its own weight based on this height. That is like I explained before, that's how it calculates. For this height, what is the weight? For this height, what is the weight? For this height, what is the weight? So let's call this weight which is predicted by the model as weight predicted. This is my weight actual and this is my weight predicted. Okay, now residuals, or is it errors? Normality of errors. So now let's calculate the difference between my actual weight and what is my predicted weight. Okay, so let's call it as errors or residuals. It can be called both as errors as well as residuals. So just don't get confused if you hear the term residuals. So that means that is nothing but the difference between my actual weight and my predicted weight. Okay, so let's, if we calculate the difference, so this is the difference. Now what this means is, what is normality of errors means, a residual error should be normally distributed. If I plot it on a graph, then these values has to be normally distributed. So you guys know, I mean, how a normal distribution looks like, right? Something like this. You have seen this graph before, right?
Yeah.
Okay, so yeah, so that is the second assumptions. That is, if I plot my residuals on a graph, then it has to follow a normal distribution curve like this. Okay, so you can see a residual error is nothing but my actual error versus my predicted error. So when I plot this, it should be like this. It should look like this. Okay, clear? Guys, clear with the second assumption?
Yeah.
Yeah, still, yeah,
Okay.
I think I'll take some time to think about it. I got what you're saying. So you're saying
Okay.
that the residual errors will be in the first quartile, third quartile, and all that, right? It will follow that.
Yes, most of your values should be somewhere around the mean value. That is, you have these values, right? You have these values now. So if you plot it, most of the values should fall near the mean of that error. That is the residual errors. Okay, so for example,
This example, yeah. Now we have height and weight.
okay, so
Predicted weight. Okay.
okay, this is my predicted.
So how this one?
Okay, so sorry, sir, come again.
Yeah. I just wanted to know. Are we going to plot this? We have -1.
Okay, I'll just show you how, I mean, I'll just show you, okay? So we have this residuals now. Now let's calculate what is the mean of these residuals. That is nothing but -1.5. Okay, so this line, so this is nothing but the mean. Whenever in the normal distribution, if you see this line, this is nothing but the mean value. So this is nothing but -1.5 now. And next, so all these values should lie, I mean, they should follow this normal distribution curve now. So most of the
Got it.
points should be present within this bell itself.
Got it.
Got it, right?
Yeah, got it.
Okay, so that is my second assumption.
Thank you, Nikhil. Yeah,
Yeah,
good.
no problem. So the next one is, the third assumption is homoscedasticity. Okay, what do I mean by homoscedasticity? Okay, so here you have for one second. Okay, so the actual weight is 60, and this is my actual weight, and the predict is 61, and for 50 it's 58. So almost the values are plus or minus 2, we can say, right? So but in the future you get a value like, say the height is 190 and his weight is 75, but my model is predicting it as 105. Okay, so you can see that for all these there is not too much variance. So variance in the sense, this how can I say, the spread of the data is not too much. I mean, it's almost the same, right? It's almost plus or minus 3. But in the future, for a data, you get a residual in such a way that the actual weight is 75, but it is predicting it as 105. Okay, for in that case my error or residual becomes minus 30. So the variance, as you can see, it's not constant. So that's what it says, variance of the error should be constant. Okay, so but it's not constant over here, it's almost the same. I mean, if you consider only this data set, you can say that the variance is constant, it's either plus or minus 3. But if you see at this data point, it's minus 30. Okay, so the variance of the data set has increased now. That is the spread of the data. If I plot it in the graph, the variance till now was, it was almost the same. It was almost the same. The variance was almost the same. But if I consider this, you can see that the variance has increased. That is, the spread of the data has increased. Is it confusing, or you guys understood it?
It's fine.
Yeah, so this is an outlier, is it? Yeah,
Yes,
understood.
it's kind of an outlier. I mean, but this was a mistake from model actually. But we cannot say it was an outlier, but yeah. So the variance is, it's huge. It's not right. It's not constant. Okay, so that's the third assumption. That is homoscedasticity. That is my that is my assumption, saying that the variance of the error will be constant. Okay, so you can check this diagram. You can see that it's almost the constant variance. This is my homoscedasticity. So heteroscedasticity is nothing but the opposite of homoscedasticity. So if you see, there is increase in the variance here and there is decrease in the variance here. So these are actually violating my assumptions of the linear regression. So we always say that linear regression follows homoscedasticity. Okay, clear?
Yeah.
Okay. So, okay. So the next one is, so the last assumption, or so the next assumption is no multicollinearity. So what do you mean by multicollinearity is? So okay. So instead of two variables. Let's say I have three variables: gender, height, and weight. So these are my independent variables, gender and height, and this is my these are independent, and this is my dependent variable. So in this case, I have two independent variables. Okay, so multicollinearity means what multicollinearity is, there should not be any relationship between my independent variables. Okay, so let's say there is a linear relationship between height and weight, and there can be a linear relationship between gender and weight, but there should not be any relationship between gender and height. Okay, so the reason could be, so the reason is, the model will get confused saying that, okay, my height is increasing, I mean my weight is increasing, but it doesn't know like whether is it increasing because of height or gender, because as the since my gender and height are linearly correlated. Okay, this might be confusing. Let me take one more numerical variable itself. Okay, so let's consider only three for now. So if age and weight height are linearly correlated, so as age increases, my height also increases, and as age decreases, height also decreases. So my model doesn't know, because as the age is increasing, my height is also increasing. So it doesn't know whether my whether my weight is increasing, is it because of age or is it because of height? So the prediction could be wrong. The predictions could go wrong. So that is why there should not be any relationship between your age and height. There has to be exclusive relationship between your height and weight and age and weight, but not between these two. So no multicollinearity means no relationship between independent variables. Clear?
We may have very few examples of that kind, right? Because there is always a relationship.
Yeah, there is almost always a relationship. Yes, so that is one of the disadvantage. So for that case, we have various measures that we can take. I mean, there are some extensions of linear regression, lasso regression. Uh, there is one more, lasso and Rich, something like that. There are some extensions of linear regression. So what they will do is they will try to suppress the effect of one of the variables. So yeah, don't worry about that, but just remember the assumptions for now. But we can see that in the future. Okay, so there are some extensions of linear regression to overcome this specific problem, multicollinearity. Okay, so but the concept is clear, right?
Yes, Nikhil, thanks.
Okay. Okay, so let's move on to how uh, the linear regression actually works. So the concept. Okay, so the linear regression actually works based on the concept called as least square method. Okay, so let's see what is that. Okay, so what, I mean, why do we use least square method is to fit our best fit line. So the basic theory behind it to fit the best fit line is called as least square method. Okay, so how it works is, okay, so I have this data set X and Y. Okay, so this is my independent and this is my dependent. So I have this data points which I have plotted on this graph. Okay, so now let's try to fit a best fit line. Okay, so initially how it will start is it will randomly plot a line like this. Okay, So it will plot like this, but it's currently it's not passing through all the points. I mean, at least it's not passing through most of the points. So what this will do is it will calculate the distance, or you can say the residuals. Okay, so what is residual here? This is my actual point. Let me try to maximize, zoom it. Okay, so this is my actual point, but if I try to predict the value of this based on the value of x, then it is somewhere over here, right? So this difference becomes my residual. I mean, are you guys with me till now?
Yeah.
Okay, so it does that with all the points. It will calculate the residuals or the errors with all the points. So this could be plus 10 and this could be minus 10. So like that, if there are 100 points, then it will calculate the error for all the 100 points. Okay, so now it has the residual. So after that, what it will do, it will start to minimize some residual. Let's take this example itself. Okay, so sum of squared errors. So let's first take the square of errors. That is nothing but, this is nothing but square of this. Let's remove this line from. Okay, so what I have done is I've just squared the error. I mean, these are my residuals, and this is my sum of my residuals. No, sorry, square of residuals. Okay, so now let's try to calculate the sum. Okay, sum of all these values. So this is my sum, 95. Okay, so it will keep this value for now. And now what it will do in the next iteration, it will fit a different line. Say like this. Okay, and after that again it will calculate the sum of squared errors. So in this case it could be, let's say 85. Okay, and again in the next iteration it will fit a line like this. Okay, like that it will try to fit all the possible lines, and it will calculate the sum of squared errors for all the all the lines. Okay, so if you see the sum of squared error, so if you, I mean, if you carefully go through this, this is nothing but sum of squared error. So squared error is this one, the square of my error. So sum of squared error is, I'm just summed all these values to 95. Like this, it will try to calculate for all the lines. Okay, and after that, it will get me the the sum of squared error for all the lines. This is for, let's say, L1, line 2, till line 10. Okay, so from line 1 to line 2, you can see that there is a decrease in sum of squared errors, and from line 2 to line 3 again there is a decrease, like that, decrease. So till line 7 there is a decrease in your sum of squared errors, but when you come to line 8 there is increase in sum of squared errors. Again it will go to line 9, sum of squared errors has increased. Okay, so it will try to fit all the possible lines on the graph. Okay, and after that it will check for a least sum of squared error value. Okay, so here my least sum of squared error value is 50, so line 7. So line 7 is considered as my best fit line. Okay, so this process of fitting my best fit line based on least squared error is this method is called as least squared error. Okay, clear with this? How did I come to my best fit line?
You're seeing that specific line that has the least total.
Least sum of squared error, which has the least sum of squared error. This is my best fit line. So the theory of least squared error is that only, that is, it is trying to minimize the sum of squared error by trying to fit all the possible lines, and after that it will get me the least sum of squared error as my best fit line. Okay, clear? Are you guys clear with this?
And so to find the best fit line, is the least square error method is used?
Yes.
Okay.
Okay, so this is the theory that least square. The theory behind linear regression is least square method. Okay, so this least square method tries to minimize the sum of squared errors to fit my best fit line. Okay, any doubts? Guys, any doubts?
I think I'm good.
One thought.
Yes.
Now the residual errors, I'm still thinking how we can come up with the various different lines. Maybe the computer will automatically find the best.
You don't have to do anything with it. Okay, there is simple line of code in R or Python to build a linear regression model. So you don't have to worry how it is actually fitting the line, but you should know how linear regression is actually working in the backend.
Because right now, we have only one line based on, and that residual error is based on the weight predicted and the actual weight.
Yes.
Okay. A different line. Is it the prediction when the algorithm or rule that we use to predict, when we have a different number for prediction, that time it will be in a different, it will come up with a different residual value, is it? Is that how it will come with multiple lines?
Yes, so I'll just take you
so
through.
Multiple L1, L2. Now in this, just considering this,
okay,
now I have L1, which is 95, based on the weight predicted. Now L2 will be 85 if I a different value, like instead of 167 for 61, like column C, I'll have a different prediction algorithm. That time I'll have line L2. Is it?
Yes, exactly. Okay, so why is it my value is decreasing? Because it is trying to predict the correct values. So let's say here my weight was 58 and here it actually predicted it as 55 in the line 1, but in the line 2 it might have predicted it as 56. So you see my residual has actually decreased from 3 to 2. So that is why my total sum of squared error has decreased. Okay, so these are not multiple linear regressions, but it's one model. But to fit that, to build that model, I need my best fit line. But it doesn't know. I mean, it cannot get the best fit line at one shot. So what it will do is it will fit all the possible lines, and out of that it will pick only that line which has my least error, least squared error. So finally it will give you the output saying that, so this is my best fit line. You can use this line to predict your weight.
Got it. Okay. So in future we will use the that particular prediction algorithm that gave me the best.
Yes, best fit line. So again,
so much.
yes. So again and again, you don't have to worry about any of this. Okay, so these are already built in. So whatever you get in the end, so that will be your best fit line. So you won't get these or these. You will get only this line. Okay, so you don't have to choose. Okay, so where is my least sum of squared errors? So 50. So I have to use this line itself. It will, I mean, it will discard all these lines, and it will retain only that line which is my best fit line. So and after that I will use this line to predict my weight.
Future weight predict.
Yes.
But in case the residual error, now like we had a case where it was 30, the residual error was 30. So in case it encounters something like that, then it will modify the best fit line. Again, it will go through this exercise to find the best fit line.
No, training happens only once initially. So that's why in the real world scenarios, what happens is they keep on training the model. Like there is a fixed schedule. So every 6 months, they'll get the data and they will train the model, because the data might change, right? So that's why.
Yeah.
So the training happens only once, and after that, I will use that that line to predict the values. If you're not getting accurate values, so what you can do is you can again change the data. That is whatever new data you get, to train the model on that, and after that you use that model to predict your values.
Got it. So this is what you were saying when you initially started this class, saying that based on the mistakes, the machine not
Exactly.
This is how it will auto.
Yes.
Got it. So once in 6 months, that's called training, is it? Where it will auto.
Yeah, it's not for all the models. Okay, so
based on the business that is using it.
Yes, exactly.
Critical, like defense planes or something like that, then they may use it more frequently. But something it is for a retail sales, then it may be once in a year, as you say. So
yeah, something like that. Okay, so when I said based on the experience, okay, yeah, you can consider that example as only. Okay, so retraining the model again and again based on the new data to just
depending on the business criticality.
Yes.
Got it. So it may be once in 6 months, once in a year, or once in 5 years.
Yeah, it depends. Because if the company is getting huge amount of data on a daily basis, then they can do it weekly basis as well, because the data is changing so much. So they have to keep their model updated. Okay. Yeah. So
one question I have is, you have all this L1, L2, all different lines. So basically we just had one data set. That's why it was at 95. So you need multiple data sets to get the rest of the lines.
No, I have only one data set over here. So okay, if you look at this, I have only one data set. On the same data set, I'm trying to plot multiple lines, because I don't know which is my best fit line now, or which is that line which is passing through most of the data points. So I will fit multiple lines on the same data set, and I will calculate my residuals for all the lines. Okay. And based on that, I mean, whichever the value is least, so this will tell me what this actually signifies is, so since my the error is least, which this means that my line is passing through most of the data points. That is my actual, the difference between my actual and predicted is the least. So I can say that I can use this line to predict the new weight based on the height.
Okay.
Okay.
Thank you.
Yeah.
And I think there are two more factors to get this best fit of line, is the intercept and the slope as well, right?
Yeah, I'll come to that. I mean, this was the
okay.
Yeah. This is just the visualization. So mathematically, it works actually in different ways. I'll come to that.
Yeah. Okay.
So okay. So before going forward, you can see that I actually took a square of this error. So can you tell me, like, why didn't I directly add the errors itself? Why did I take the square first and then I added it?
To minimize that negative values.
Yes, exactly. So suppose, let's say, so the errors is -1 here, and if I have the +1, so these are actually, yeah, these are, I mean, it becomes 0,
Yeah.
right? So that's why. So what I'll do is, I'll just take a square of it first, and then I'll find the
Yeah.
sum of
It will
square.
cancel out the negative values. Yeah.
Yes, yes, exactly. Okay. Okay, so before going forward, I have a question. So let's say I have a data set X and Y, and these are my data points. So I want to build a linear regression model on it. So where will you draw the best fit line for this data set?
It may come in between.
Yeah. In the
45
between
degrees.
these both
Okay,
data points.
each one of you can tell me your answers. Okay, so Bhavana, you're telling it's somewhere around here, right?
Correct.
Okay, any other answers? Like, before just think, I mean, whatever we studied till now, all the assumptions, all the definitions of linear regression and the least square method. So just have a, I mean, just think about it and just tell me the answers again. Or if you want to stick to it, then just stick to it. But just think about it for a minute and then let me know the answer.
Or maybe depending upon the least square value, like where we get the least value of that.
Okay, so visually, I think, I mean, visually, let's not get
Yeah.
into the, so visually,
Okay.
so you're saying, so this is your best fit line.
Yeah.
Okay.
Yeah.
It should also be a point that touches maximum number of, a line that touches maximum number of points.
Okay.
And this one touches 0.
Okay. So where do you want to plot it?
I'm still thinking.
Okay. You can take your time.
Yeah, the top, the 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 points above this line have 8 dots.
Okay.
And whereas below this it's 7.
Okay.
And
I'll
it
plot
will
it.
form a line touching all those 8 points top. Okay, you draw.
Yeah. Now tell your answer.
Okay, so both have equal now.
Yeah.
So in that case, yeah, then I'll stick to
This one. Okay. Sutapa, you have any other answers?
No, I'll stick to that one.
Okay. Let's go back to the assumptions of linear regression. Linearity. Okay. So here, if I see, as my x increases from this point to this point, you can see y is also increasing. But as I go from x, this point to this point, you can see my y is decreasing. As I go here, again, as I go forward, my y is increasing and again it's decreasing. So I can say that the data is I mean, it's not linearly correlated. So can I use linear regression on that? Can I fit the best
No,
fit?
I didn't get it. The second one where he said that as the x is increasing,
My y
y.
should also increase.
Oh, okay.
So here, if you see, the variation is like this,
Yeah.
increasing and decreasing, right? So I cannot use my linear regression on this.
Hmm. Good. Yeah.
All right. So always it's, I mean, it's very essential that we should remember all my assumptions of the regression. I mean, these assumptions are only for linear and logistic regression. For highly more sophisticated machine learning algorithms, you don't have any assumption. These are the few drawbacks of regression models, because we cannot guarantee that the data set that you get in the real time, I mean, we cannot say it's always linearly correlated, right? So yeah, but if if your data satisfies all the assumptions of linear regression, then linear regression is the most powerful algorithm that we can get. Even I mean, even today, most of the companies, they use linear regression to model their data, because it's highly powerful, linear regression, that I can say. But if it doesn't satisfy the condition, then the results are not that accurate. Okay.
Yeah.
Okay. So now let me fit the best fit line again. So let us consider that based on the data set, and after fitting the best fit line, this is my best fit line. Okay, so now we need a way to represent this mathematically, because machine doesn't know, I mean, how to what can I say, how to plot it or anything. I mean, it doesn't actually look at the plot; it actually solves it mathematically. Okay, so let's try to build a mathematical equation for this line. Okay, because tomorrow, let's say you have that line, and you have height, and you want to predict your weight. You cannot every time go back to the graph and plot exact lines, horizontal and vertical lines, to get your output, right? So we need a way to to represent this line mathematically, so that you can, I mean, whenever you want to predict something, you can just impute the values into that equation to get your output. Okay, so have you guys come across equations of a line before? I mean, actually,
Yeah, that is y is equal to
Y is
mx plus c.
yes, exactly. So the equation of a line, we can say, is mx plus c. Okay, so y is nothing but my dependent variable, that is my y-axis, and x is my x-axis value, m and c. So let's see what are these m and c. So m is nothing but my coefficient.
Slope.
Yes, slope of the line. So we actually call it as coefficient. So yeah, but actually it's a slope of the line. But whenever you build a model, you want to say it as coefficient. Okay, coefficient of this particular variable. And the c is nothing but my intercept. Okay, so this is my y, this is my x. So that how can I find the slope of this line is m is equal to tan of y divided by x. Again, you don't have to worry about the equation at all, because you don't actually do this, but the algorithm works like this. Okay, so it will fit this line, and it will find what is the slope of the line, that is tan of y divided by x. Okay, so that is my m in this line, that is my m in this equation. Okay, so let's say for the sake of simplicity, let's give a value. Y is equal to let us consider it as 1.3. I got the value of m as 1.3 x plus, so c is nothing but your intercept of the line. So intercept is the difference. So let's say this is your best fit line and it is passing through y at this point. Okay, so this vertical distance between this and the origin is called as intercept, or in my equation it is called as c. Okay, so but if your line actually passes through the origin, then you can say that your intercept is 0. Okay, so again let's consider that my intercept for this best fit line is 2. Okay, so it is 2. So I have fit the best fit line. So I have the line. So this is the equation of that line. So my slope, that is m, is 1.3 plus, so plus c is my intercept. Okay, so I have this equation now. Suppose I want to predict what is my height, what is my weight for a particular for a particular height. So I can simply use this equation now, right? So y is equal to, I don't know the value of y, so y is equal to m is 1.3 into whatever height you want to, whatever there is height. So let's say I have the height of 180 plus 2. So the value of this should be your height, should be your weight. Okay, so what we did here, we just converted this best fit line into a mathematical equation, so that every time we want to find out the value of weight, we can simply put the value of this height into this equation to get the value of weight. Okay, clear? You want me to explain it again?
I'm good.
No, that's fine.
Okay. Okay, so yeah, that's how it works. So you will whenever you fit a linear regression model, we will call it as coefficient, so don't call it as slope. So call this m as coefficient. So we will get this coefficient and we will fit an equation like this and we will get the value. Okay, so that's the whole working of linear regression model. Okay, any confusions? Any doubts?
Can you give a real life example where this
Okay.
linear regression model is used?
Okay. Okay, I can give the example that I actually worked on. Okay, I'll give you the practical that I actually work on. I actually use linear regression model in my day-to-day work. So, for example, you know all the logistics, like let's say let's take an example of Amazon company. Okay, so they have so many goods that they want to transport from one place to another. So like that, those transportation actually happens, lakhs of transportation happens per day across the globe for them. Okay, so they have so many variables. So let's consider them as x1, x2, x3, x4, and the dependent variable is the shipment cost. Okay, the shipment cost is my dependent variable. So what their requirement is, so they want to, so let's say this is the beginning of the year and they want to predict what might be the shipment value for these many variables. So let's say if I go to this particular carrier, okay, so there is a carrier ABC. So if I go to this carrier, what is my shipment cost? So if I go to that carrier, what is my shipment cost? If I go to this route, if I take this route, what would be my shipment cost? Like that, they can, they can perform multiple permutations and combinations using this equation, linear regression equation, to identify what is the least shipment cost that I have. Okay, so this this shipment cost is calculated based on the linear regression model. So they will see which is that carrier who is giving them the least shipment cost, and they will go to that carrier and they will take that route, etc., etc. That is one of the examples. So there are so many examples, like wherever there is a numerical variable to be predicted, then we can go for linear regression. Okay.
Thank you.
You can take an example. So example of superstore as well. So they want to predict what might be their sales in the future. Okay. So they can give all their independent variables to predict what might be the sales for the month of, let's say, so today is October, so they want to predict their sales for the month of November, so that they can have all those supplies in their inventory. So they will go for linear regression model. So they will input all the independent variables and they will predict, so this is the sales, so the sales is going to be high, so I need to maintain my inventory, I need to maintain the stocks in my inventory. Okay. So yeah, so there are so many applications. See, so these are the few. So wherever there is a numerical variable that has to be predicted, you can go for linear regression model. Okay.
Okay, thank you.
Okay.
So this wouldn't be unsupervised learning. This will be supervised only, is it?
Yeah, this is supervised because I
When
have.
we have,
Yeah, go ahead.
no, you only go ahead.
Okay.
Yeah, I think I may have forgotten what is unsupervised learning. So unsupervised is when we have too many variables, right? When we do not know many things.
No, we don't have target variable in that. That is, we don't know what to predict.
Got it. Okay.
We don't know, because here I know what to predict. I need to predict weight, so I use linear regression. But in the unsupervised learning, I don't know what to predict. I just want to cluster, right? So we cannot use linear regression for that. Linear regression comes under supervised learning.
Okay. Okay. Maybe if I get to solve something.
Yeah, obviously, yeah.
Example.
Yeah, so this is the first class. I mean, you get confused. Because in the coming all the classes, I mean, we'll be dealing with only machine learning algorithms. So as we go on solving different algorithms for different data set, then you will understand, okay, we use this for them.
Yeah, thanks, Nikhil. Yeah. And we'll be using Python or R?
We actually do it in Python, but if you guys want, I can simply show you like how to do it in R. It's not a big deal. I mean, it's just a one-line code.
Oh, okay.
Okay, I can do that in R as well. I'll build a linear regression and logistic in R. So, and the rest of the machine learning algorithms will do it in Python. Okay. All right. So, any questions, or shall we go ahead?
You can go ahead.
Yeah, I'm good too.
Okay.
I'm still confused. I'm sorry.
It's okay. What is it?
Considering the Amazon, you said, now reducing shipping cost, it will be, it's difficult to even find non-collinear, non-related independent variables, right? Now, if I want to see my shipping cost, if I want to predict my shipping cost, it also depends on the warehouse location. The warehouse location should be maybe in central India or some central part. So
Yes.
so then that will be, anyway, maybe we'll see when we see the examples. Yeah.
Yeah, maybe. Yeah, when we do the.
I'll have this question. Yeah.
Yeah. So yeah, actually, when we work on the actual data, then you'll be able to relate it. Okay. So let's move forward. So, okay, now you have the model, you have the linear regression model for now, but you don't know, I mean, how how your model, will perform. So we always need evaluation parameters. Okay. To measure the performance of your model. So all the models will have model evaluations or model evaluation parameters. So we always have to, whenever we build a model, we always have to do this step. That is to evaluate our model. We need to check how our model will perform, in the actual scenarios. Okay. So for that, we have multiple parameters based on which we can say that, okay, this model is pretty good, so we can go ahead with this model. Or, okay, so this model is not, it's not up to the mark, so we cannot move ahead with it. Okay. So for that we have basically four, for linear regression, we have mainly four evaluation parameters. Okay, so one is R square, adjusted R square, root mean square error, RMSE, or mean absolute percentage error. Okay, so let's see one by one what are those. Okay, so the first one is R square. You don't actually know the math behind it. What is this RSS? What is TSS? But because these, I mean, whenever R or Python builds a model, it will give you all these values: all R square, adjusted R square, RMSE, and MAPE. Okay, so but just for your understanding, you can say that R square is calculated using this formula: 1 minus RSS divided by TSS. So what are RSS and TSS is the amount of variance in the response or dependent variable. Okay, it's too confusing now, so I don't want to get into this. Probably when we build a model in R, I'll explain what are these, what are what are TSS and what are RSS. Okay, so for now, just understand what are the characteristics of R square. Okay, so the range of R square actually lies between only 0 and 1. So 0 is the least value, 1 is the maximum value. Okay, how to interpret, I'm just explaining how to interpret the values of R square. If the value of R square is 0, that means your model is not good at all. It means that the prediction power of your model is 0%. Okay, so whatever the value your model predicts, its accuracy is 0%. It's not correct at all. Okay, so if your R square value is 1, that means your prediction power of your model is 100%. Okay, so let's say if it predicts the weight as 60, and if the value of R square is 60, if the value of R square is 1, you can say that, okay, so the predicted value is 60, so the actual value is also 60. It's exactly the same. Okay, now suppose if your R square is, I mean, between 0 and 1, let's say the value of R square is 0.8, then that means you can say that the value predicted from my linear regression model is 80% correct or 80% accurate. Okay, so let's say my weight is predicted as 60, so I can say that it's almost 80% correct. Okay, clear how to interpret this?
So if it's 0.5, then it's 50%.
Yes, you can say your model is 50% accurate. Okay.
So generally, what percentage we should keep for the accuracy, or depending upon that data and what are the requirement from that business?
Yeah, it actually depends on the business, because in my case, the R square is around 0.6 or 0.7. So even if my accuracy of model is 60% or 70%, I can say that my model is pretty good. But in some cases, it has to be around 80 to 90%. Only then they will accept the model.
Okay.
Okay, so it depends on the business.
Okay.
Okay, so yeah, so that's how you interpret your R square. So the next one is adjusted R square. So we actually use adjusted R square because there is a limitation of R square. So what that limitation is, let's say, I have six dependent variables. Six independent variables and one target variable. So the value of R square could be, let's say 0.8. Okay, and now if the variables, the number of variables increase from 6 to 8, then my linear regression model, it doesn't care whether these variables, that is 7 and 8, are they important or not, are they influencing in any way to predict. Okay, R square doesn't check that, so it simply increases the value from 0.8 to 0.9. So in this case we are misleaded now. Okay, so without 7 and 8 my R square value was 0.8. So after I included these two variables, okay, my accuracy has increased to 90%. So what we'll do, we'll go ahead with all the variables, but in the actual scenario, x7 and x8 are not influencing y at all. They are simply dummy variables in my data set. Okay, so this is misleading, right? So this is a limitation of R square. It doesn't care whether the variables are adding any value to the model or not. So they simply increase the value of R square, saying that since you have increased the number of variables, my R square is increasing. So to overcome this problem, we have a slightly adjusted form of R square called as adjusted R square. Okay, so how this varies is, so if in the first case, that is, let's consider only 6 variables, x1 to xs. So in that case, both my R square is and adjusted R square are 0.8, 80%. Okay, but now in the second case, in the second iteration, let's add x7 and x8. Okay, so but x7 and x8, they don't have any influence on my dependent variable. They are simply junk in the model. So we should never include junk in the model. It's not good. Okay, so adjusted R square identifies that x7 and x8, they don't have any influence on y. So there is no point in including these two. So it penalizes the R square. That is, the value of adjusted R square in the second iteration will be 0.7. Okay, so this gives us an indication saying that, okay, in the first iteration it was 0.8, but in the second iteration, after I included x7 and x8, my adjusted R square is actually decreasing, which means x7 and x8 are junk. That is, they don't add any value to my model. So they are just junk in the model. So I should remove these two. So you'll go back to iteration 1, saying that I want only 6 variables in my model. Okay, so always use adjusted R square to measure the accuracy of your model. I mean, it's not completely different. It is derived in the same way of R square, but adjusted R square is just a slight modification of R square. Again, the math of it is slightly out of the scope. So, I mean, you will get ready-made values of both R square and adjusted R square. So just understand how to interpret the values. So if this is the value, so this is the conclusion. If this is the value, this is the conclusion. So always use adjusted R square to measure the accuracy of your model. Okay, clear?
So is it better to use adjusted R square?
Yeah, always use adjusted R square itself. Don't use, I mean, the model will give you both the values, adjusted R square and R square, but okay, why it will give you both these values is, it means that if you see this iteration, you can see that R square value is 0.9, but adjusted R square is 0.7. That means there are some junk variables in your model. So okay, what this is suggesting is, you need to go back and inspect what are those junk variables. Okay, and if you see this, you can see that both R square and adjusted R square are almost same. So that means all the variables they have some value, they're adding some value to my model, and I want all these variables to be included in the model.
So should we get rid of those two junk variables?
Yes, we have to get rid of this. And just remember the theory now, because when I implement this in R, so you will be able to relate that. But yeah, So if you see that there are junk variables in your model, you have to remove those junk variables, and there are many number of ways to identify which are the junk variables. Okay, but yeah, you should remove all the variables that are not adding any value to your model. Okay, is it clear?
Yeah.
Okay, so why we are telling that these are junk variables is, see, the motto of machine learning models is garbage in, garbage out. That means if you feed quality data into our model, then the results obtained from the model are, I mean, they are very high. I mean, the accuracy is very high. But if you put all the garbage into a model, then the results are, they're not accurate at all. Okay, like I said, you can go back to the the example comparison with the kid. So whatever you teach the kid, it assumes that it will learn that whatever you teach. Similarly, let me give you an example. 2 into 1. So let's say I have this data set. Okay, these are just tables of 2, and I have something here. Okay, so the values are correct, but if you see this particular row, it means that it is saying that 2 cross 9 is 60. Okay, so we are feeding this into the model, but I mean, because the model will learn whatever you tell it to it. So whenever in the future, if you ask what is 2 cross 9, it is going to say 60. So this is noise, or we can say it has a junk or garbage, whatever you want to say. So this is noise in the data set. So you should always correct it, or you should remove it. Do not include all the junk data in your model. Include only the quality data. Okay, as the quality of your data set increases, the accuracy will it will go on increasing. Okay, so that's what I meant here by, I mean, when I said junk, that X7 and X8 are actually confusing the model. They are not adding any value, but and after that, more than that, they are just confusing the model. So remove X7 and X8 and include only these variables. Okay, clear?
Yeah.
Yes.
Okay. So yeah, so that's about R square and regression. So whenever it comes to linear regression, you don't actually go to RMSE and MAPE. You mainly look at R square. Sorry, adjusted R square. So if your adjusted R square is high, then you can say, okay, my model is pretty good, so I can go ahead with it. Okay. So yeah, so this is the modified version of adjusted R square. Again, it uses the R square as well, but it is actually taking number of predictors into consideration. So previously it was only 6, but now there are 8. Right, so it will take that as well into consideration, and it will calculate my adjusted R square. Okay, so don't scratch your head around this formula and all, but just know how to interpret it, because that's what important, not the math behind it. Because these are all the ready-made values. You will get it whenever you build the model. There are so many tools to calculate it. You don't have to remember the formula and calculate the values. Almost all the tools will give you the values. Okay. Yeah. So the next one is root mean square error. So this is slightly the extension of sum of squared errors that we saw, when we were fitting the best fit line. So the formula is predicted, the summation of predicted minus actual whole square divided by the total number of data points. So if I have 1000 data points, so in this case I had Okay. 7 data points. So in this case, my n becomes 7. So how I can calculate it is, I have the residuals, I have the sum of squared errors, that is 95. So square root of 95 divided by, what is the number of data point? What is the number of data points in my data set?
7.
Yeah, 7. Okay, so 3.68. This is my root mean square error, 3.68. So that means the average error, you can say that it's varying around 3.6. Like if your predicted value is 60, then you can say that, okay, so since my RMS is 3.68, the actual value could be somewhere around 63 or 57. Okay, so that's how you can interpret. But we don't usually use this RMSE, but if you want to, you can interpret it like this. Okay, so we should always try and minimize this RMSE. So in this case, it's 3.68. Okay, in the next case, in the next iteration, if it is 2, then you can say that, okay, your model's accuracy has improved. That is, so if the value is predicted value is 60, then you can say the actual value might be around 62 or 58 because the RMSE is 2. Okay, clear with RMSE?
Yes.
Okay, but there is one drawback of root mean square error, that is its value goes on changing as the range of your independent variable, or sorry, dependent variable increases. In this case, okay, uh, my dependent variable is weight, so the values will be somewhere around 60 to 70. But what if my dependent variable is sales? Then the values could be in lakhs or crores, something like that, right? So in this case, my R square value could be something like this. So it's very difficult to, interpret. I mean, okay, so RMSE is this, so we don't know, is it a good RMSE or is it a bad RMSE, right? So it's very difficult to, that is one of the disadvantages of RMSE. As the range goes on changing, its value goes on changing. There is no fixed value. For example, in case of R square, you can see that the value lied between 1 and 0, but that's not the case with RMSE. There is no limitation to that value. It can be anything between 0 and infinite. Okay, so that's why we don't usually go for RMSE. We go for adjusted R square. But it's a, what you can say, it's a good metrics if you want to measure between the iterations. So what do you mean by iterations is, let's say, let's go back to this example. I have 6 variables. Okay, I will include only these 6 variables and build the model first. So this is my M1, model 1. Remember, these are not lines, so these are models. So all these lines are built within this model. So this is my best fit line, and this is my model 1 for these 6 variables, x1 to x6. Okay, in the second iteration, I will use x7 and x8 as well. Okay, x7 and x8 as well. So this is my M2, this is my model 2. So this is my iteration 1 and this is my iteration 2. These are my model names, these are my R square values, these are adjusted R square values. Okay, so here RMSE value is, let's say, 3.6, and in this case RMSE value is 4. Okay, so you don't know what is the best RMSE. Is it 3.6 or 3000? But if you look at these two iterations, you can see that your RMSE has increased from 3.6 to 4. That means whichever RMSE is less, you should go for that model. Okay, so you can use this metric to compare the iterations to identify which is the best model or which is the best set of variables that I can use to build the model. But it's not a ideal evaluation parameter to to measure the accuracy of the model. But to measure between the iterations, to measure the accuracy of the model, you can go for RMSE. Okay, clear? Nice. Any doubts?
Yeah. No.
Okay. Okay. So yeah. So in order to overcome that, in order to overcome the disadvantage of RMSE, that is the range, we have MAPE. MAPE is nothing but, I mean, it's an extension of RMSE again, where we'll just try to find the percentage of the value. Okay, if you see, it's the same formula without the square root. I mean, of course, without the square root, it's the same formula multiplied by 100. That is, it's in the form of percentage. Okay, so just know, actually, I mean, that these are the evaluation parameters, but we don't usually use it when evaluating the model. The main one that you need to understand is adjusted R square.
So we don't use MAPE also, though it is now in percentage format, because which means between 0 and 1.
Yes, you can use it. I actually never used it, but yeah, I know it's a percentage. It's a percentage form of RMSE, but I don't know.
It's still not very popular. Got it. Okay.
It's not very popular. Most of the people prefer adjusted R square only because it's a standard one. That's why.
Okay. And if you can, yeah, does this say? Okay, it doesn't say why MAPE is not very popular. No problem.
I don't know. I mean, most of the I have seen so many organizations, they just prefer adjusted R square value.
R square, adjusted R square. Got it.
Okay. So yeah, so these are a few of the evaluation parameters for linear regression. So any doubts till now?
No.
We just have to review it one more time afterwards. Do
Yes,
everything to sink in.
Yeah, maybe. Okay, so for now it's okay, right? So at least getting the theory behind it. Okay.
Yeah.
Okay, so the last concept is multiple linear regression. So this is nothing but the extension of linear regression. So whatever.
One quick question, Nikhil. Sorry.
Yeah, yes. Tell me.
Most popular, you said R square or adjusted R square or both?
Adjusted R square. Yeah, but people actually use R square as well, just to compare between adjusted R square and R square, so that if the difference is more, that means there is some junk in your data set. So adjusted R square is either equal to or less than R square. It's never greater than R square. Okay.
Can you repeat that statement, please? Okay. Adjusted R square is what?
Adjusted R square is either equal to or less than R square. It is never greater than R square. Okay, so let me just type it over here. Adjusted R square is less than or equal to R square. Okay, it's never greater than R square. Okay, because if it is equal, that means all the variables that I have in my data set, they are, they make sense or they add value to my model. But if my adjusted R square is less than R square, that means there is some junk in my data set.
Right.
Okay. Yeah. Okay. So coming to the last topic, multiple linear regression. Okay, so here I have only height and I want to predict weight. That's what we did when we were fitting the best fit line, right? So, but what if there are other variables? What if I have age, gender, or if it's a school data set, then I might have class. What is the class of it? What is the section? Something like that. Okay, so in this case, I have 5 independent variables and 1 dependent variable. And when I fit a linear regression model for this, that becomes my multiple linear regression. So we don't refer to it as multiple linear regression, but it's just a concept. Under linear regression, we have 2 types: simple and multiple linear regression. Okay, so these are the 2 types of linear regression. The simple is nothing but we will have only 1 independent variable and 1 dependent variable. The multiple, we will have multiple independent variables and only 1 dependent variable. So the equation will become like this: y is equal to m1 x1 plus m2 x2 plus m3 x3 etc. plus c. Okay, so it will be just extended from y is equal to mx plus c to y is equal to m1 x1 m2 x2 m3 x3 plus c. Okay, so the theory behind it and all, it remains all the same. It's just my equation is extended into include all the variables.
So so now I'm guessing that with respect to the Amazon example that you used, where you're finding the least shipping cost, maybe multiple linear regression equation might be used, right?
Yes, obviously. I mean, in real calculus, you don't actually build simple at all, because
Okay.
it's
Always multiple. Okay.
Yeah, it's always multiple, because there are so many variables that actually, that I can actually use, because if I use only height to predict weight, then the prediction power of the model might not be that good. But if I use information like age, gender, and class, then the prediction might go up, the accuracy might go up because of age, gender, and class and all. Right. So you always try, we always build multiple linear regression in real time.
So is it always one dependent variable, or you can have more than one?
No, it's always only one dependent variable. Okay, it's always only one dependent, but the independent variables can vary.
But in this multiple linear regression, so all variables should be linearly like related to each other or something with that with respect to y.
Not to each other. It has to be linearly correlated with weight, with
Wait, okay.
my y. Okay, what if they're intercorrelated? If my, let's say, age is correlated with height, so what does it mean? Does it violate any condition?
Yeah, that hetero viscosity.
No, multicollinearity. Heteroscedasticity is, it's okay, it happens. Homoscedasticity is the variance of the error should be constant.
Oh yeah, multicollinearity.
Multicollinearity. Yes. Okay, so I'll show you that. How to check multicollinearity and all, but yeah, there should not be any multicollinearity. If there is, then you have to remove either age or height from your data set, because else the accuracy actually decreases. So you should either remove the height or age from your model and then build the model. Okay. So, okay. So yeah, so that's about linear regression. Any questions?
I think I'm good. So about this today class, the PDF you will be uploaded on that discussion board or in the material on the blog?
That I'll check with Adarsh and I'll let you know, because I don't know actually where they upload it. I'll check with him and maybe I'll drop a mail to support team and they'll upload it.
Okay, yeah, we just want to be, because then if we have to like later like go for the revision, so at least we can just go for the PDF, not for the whole entire video recording.
Yes, exactly. I have a document as well. I'll just share it with the support team. They'll upload it.
Okay. So where we can find it on that blog?
That I need to check with him. I'll check with him and maybe in tomorrow's
Oh
class.
yeah, sure,
Because
definitely.
I don't exactly know where they upload it.
Okay, no problem. Yeah.
Nikhil,
Okay.
you
Yeah.
took the last week's class also, right?
Yeah, I took that R,
Yeah.
I guess.
Yeah, the R files that you created in class,
Okay.
post it onto the website whenever you have it.
Uh,
The program files that you created during the class, or
I'm sorry. I mean, I lost you. Were they posted, or you want me to post it again?
No, it wasn't posted. Let me chat. I think my sound quality is bad.
It's okay. I'm able to hear you. But I actually
Okay,
sent
yeah.
I actually sent a mail to
Yeah.
them.
I did find the materials.
Okay.
You did. Thanks so much for that.
Yeah, no problem.
Yeah, but
What?
the program files that you created.
Okay, yes, then. So let's wind up for today.
Yeah.
Thank you for attending the session. I hope you all enjoyed it. Don't forget to visit our Vimeo page and follow for more upcoming videos.